In the last video, I covered deviations from the mean. And the deviations, I showed an example of two different companies, Company A and Company B, where we had a list of employee salaries. So here you can see that employee salaries are 30,000, 40,000, all the way up to 70,000. Over here at Company B, we had salaries that had the same average. So both of these groups have an average of 50,000. If you work them out, if you work out the average of this set of numbers and the average of this set of numbers, you'll find that they both come out to be 50,000. But what we were looking for was a measure of variation. We wanted to be able to show in a single value. So if we didn't get to look at all the data, but just if we could come up with some way that there'd be a single value that would show that these numbers here are more clustered together. They're more clustered around 50. Over here, they're more spread out away from 50. I explained why the range was a bad idea, so I'll leave that for my description in that past video. What I want to focus on now is the deviations. It's a different approach. Now, we covered the deviations insofar as we said that deviations tell us how far any one of these numbers is from the mean. So 30 is 20 below the mean, 40 is 10 below the mean, and so on. So we get a different deviation for all of our different observations. But when we tried to come up with a single value that could describe all of the deviations, so when we tried to average out these numbers, we were left with a 0. We were left with the 0 for this set of data for Company A. We were left with a 0 for Company B's data as well. And the reason for that is that even though the deviations are very different for the two different companies, we had an equal amount of negatives as we did positives. Or rather, the negative values, when you total up the negative values, they cancel out with the positive values. So here, minus 10 and minus 20, that makes negative 30. We have positive 10 and positive 20, that makes positive 30. They cancel out when you add them up. So you're only going to get an average of 0 when that happens. Over here at Company B, our negatives and our positive values cancel out once again. Now this creates a real problem. It actually creates two problems. The first problem is we're looking for a way to measure variation. And an answer of 0, so if we're finding an average deviation, which would be to put the sum or the total over the number of deviations. So this would be 0 over 5, which is just going to be 0. So if our measure of variation tells us we're getting a 0, 0 is the same as saying that there is no variation. But we can see that that's not true. These numbers here, from 30 up to 70, there's variation in those numbers. They're not all the same number. And not only is there some variation, there's actually more variation in Company A than there is in Company B. Company B has values that are clustered around 50. So a 0 just doesn't do it. It won't work for us because it's not telling us how much variation there is. We don't have 0 variation. Also, the 0 in both of them seems to be suggesting that both companies have the same amount of variation. So that's a real problem as well. And like I said, the reason that all of this goes wrong is because the negatives cancel out with the positives when we try to take a sum. Why did we try to take a sum? We're taking a sum because we want a single value. We want an average, and averages use sums. So there's a trick. There's a way around this. It's actually really simple. If you don't want to see any negative values, you can square your values. When you square negative 20, you get a positive 400. When you square a negative number, you always get a positive result. So negative 10 times negative 10, that gives me positive 100. 0 times 0, that's 0. Positive 10 times positive 10, well, that turns out to be positive 100 as well. When you square values, the results are always positive. So now we have a list of squared deviations. These are not deviations, these are squared deviations. I'll just write that as deviation squared. When I sum these guys up, when I add them up, it's not going to cancel out and turn out to be 0. If you do this, you get 400 plus 100 plus 100 plus 400. We get the sum of our squared deviations is equals to 1,000. Over here on this side with company B, when I square my deviations, I'll get 4, 1, 0, 1, 4, and my sum of squared deviations turns out to be 10. Now, this is going somewhere, because remember before, we got a 0 for both companies. Now we get different values for each company. Let me clear this up a little bit. Okay, so for company A, we have a large number. We have 1,000. And company A had more variation. There was more of a spread between 30 and 70. Company B, we have a smaller value, and we had more clustering around the 50. We had a smaller spread. So this is looking good. If I wanted to take the average, I'm no longer going to be, actually let me, let's make a bit of space here. Okay, if I want to take my average, I'm no longer going to be taking the average deviation. Instead, I'm going to be finding the average of my squared deviations. And to do that, I'm going to need a sum, but I'm going to put the sum of my squared deviations. They use this a lot in the course. They just shorten it to the sum of squares. The sum of squares is my sum of my squared deviations. So I'm going to take the sum of the squared deviations from that column and divide by the number of deviations. So for company A, this is going to be 1,000 divided by 5. That'll be 200. For company B, so this would be for company A. For company B, it would have been 10 divided by 5. This is going to be 2, so that's for company B. Now what we can see here is that company A gives a measure variation that is larger than company B. So this is good. This average square deviation works. It shows us that company A has more variation. That's one of the things we wanted to see. It's also not 0, so it shows us that there is in fact some variation. That's one of the reasons that the average deviation failed. Another thing that works here is that we don't actually, unlike the range, we are using every single one of the values to come up with this. When we found our sum of squares, we added up every single one of the values. We added up a square deviation for every single observation. So this idea works and we keep it. We don't call it the average square deviation. Instead, this is given the name variance. The variance can be thought of as simply just being the average squared deviation. We wanted the average deviation, but it always comes out to be 0. So instead we settle for the average squared deviation. And variance is equals to the sum of squares over n. Now, you're going to have other variations of this formula. I'll deal with them in a later video. Initially, it's just the sum of squares, the sum of your square deviations over n. And so our formula looks like this. The variance is written with this symbol. It's a squared quantity, showing us that we're dealing with squared quantities. It's the sum of squares over n. This is how we measure variation in the course. The variance is an idea that works, and so we're going to stick with this throughout the rest of the course. Now, it satisfies a few things. First of all, it uses every observation. Remember, the range did not, so the variance is better than the range for that reason alone. It uses every observation. And Another thing is when we're making comparisons, when we're looking at the variance of company A and company B. So we had 200 for company A and a 2 for company B. It can be used to compare distributions. So for example, if you get a larger number for one distribution, that means that there's more variation. So bigger means greater variation. Now, the average deviation couldn't do that. The average deviation was always giving us a 0. So that's a second thing that works. And also a third thing, it's kind of redundant at this point, but it's important to note that unlike the average deviation, the variance is not always equals to 0. 0 was a useless answer that the average deviation was giving us. It basically told us that there was never any variation to be measured, even when we could see that the numbers were not always the same. In company A, 30, 40, 50, 60, 70, these numbers vary. They are not all the same numbers. So to get an answer of 0 variation made no sense. So the variance works. The variance uses every observation. It can be used to compare distributions. Bigger means greater variation, smaller means less variation, or a smaller result like a 2 means less variation, and it's not always 0, so it's always going to give us some measure. Actually, it can be 0 if I had a list of numbers like 3, 3, and 3. Well, the average here is 3, and so when I find my deviations from the mean, 3 minus my mean is 0. Again, it's 0. Again, it's 0. When I square these values, I'm going to get 0 squared is 0, 0 squared is 0, 0 squared is 0. When you sum up your square deviations, SS means the sum of the square deviations, you're going to get 0. And so when you find the variance will end up being 0 divided by 3 equals to 0. 0 means no variation. There is no variation in my set of numbers. They are all the same number. So the variance works to show me properly when there is no variation. So the variance works. It's a bit of extra work. We have to make this extra column. It's not much of a big deal. So that's great. It makes sense. It works. It gives us proper answers. However, the variance is not used as much as the next one I'm going to introduce. It's not used as much as the standard deviation.